On September 28th, 1969, just after 10:45 in the morning, a fireball tore across the sky above Murchison, a small town in Victoria, Australia. People heard a sonic boom. They saw a trail of smoke. Then, rocks started falling. Over a 13 square kilometer area, more than 100 kilograms of dark, stony material rained down. It was a meteorite fall, an event that happens, but is rarely witnessed and recovered so quickly. Some of the fragments smelled strongly of tar or methylated spirits. One piece crashed through a barn roof. At the time, the world was obsessed with space, and Neil Armstrong had walked on the moon just 2 months earlier. Samples from the Apollo 11 mission were being analyzed in labs, promising to reveal the secrets of the moon's origin. But this smelly rock from Murchison, Australia, would prove to be just as important. Samples were sent to labs around the world, including NASA's Ames Research Center in California. A team led by chemist Keith Van Volden began a careful analysis. They wanted to see what organic compounds might be inside. The process had to be meticulous. They had to prove that any organic molecules they found were from space, not from contamination on Earth. They analyzed the soil where the meteorite landed. They analyzed the hands of the people who picked it up. And they took a piece from the meteorite's core, a section that hadn't been touched by the outside world. They ground it up, dissolved it in water and acids, and ran it through their instruments. The results were stunning. The Murchison meteorite contained amino acids. These are the building blocks of proteins, the essential machinery of life as we know it. They found common ones like glycine and alanine, but also dozens of others that are not used by life on Earth. This was the smoking gun. These molecules were extraterrestrial. They had formed in space, somewhere in the cold darkness of the early solar system. But the most profound discovery came later with more advanced techniques. Scientists found tiny microscopic grains of dust embedded within the meteorite. By analyzing the isotopes of elements trapped inside these grains, they could determine their age. Some of these silicon carbide grains were 7 billion years old. The Earth is 4.54 billion years old. The Sun is 4.6 billion years old. These tiny specks of dust were older than our entire solar system. They were true stardust, forged in the atmospheres of dying stars long before our sun ever ignited. The Murchison meteorite wasn't just a rock from our solar system's asteroid belt. It was a time capsule. It carried the chemical precursors to life and the literal dust of long dead stars. It was a piece of cosmic debris that was older than the Earth itself, and it was not the only one. Number 18, the rock that carried the seeds of life. The Murchison meteorite contained over 90 different amino acids. Only 19 of them are found in life on Earth. The rock is so chemically rich that it also contains purines and pyrimidines, the compounds that form the letters of our DNA. Some of its individual pre-solar dust grains formed more than 2 billion years before the sun itself. The story of the Murchison meteorite began with a boom and a shower of stones, but its scientific story began with the careful, painstaking work of separating what was alien from what was terrestrial. When scientists first detected amino acids in the rock in 1970, the big fear was contamination. Maybe the amino acids were from the Australian soil, or from the hands of the farmers who picked up the fragments. To rule this out, they looked at something called chirality, or handedness. Amino acid molecules can exist in two forms that are mirror images of each other, like a left hand and a right hand. Life on Earth exclusively uses left-handed amino acids to build proteins. The Murchison meteorite contained a nearly equal mix of both left-handed and right-handed forms. This random mixture, called a racemic mixture, was proof that the amino acids were not from earthly life. They had formed through simple, non-biological chemistry in space. This discovery changed everything. Before Murchison, the origin of life on Earth was a puzzle confined to Earth itself. The prevailing theory was that life's building blocks formed in a primordial soup on the young planet. Murchison showed a different path. It showed that the building blocks of life were not unique to Earth. They were common in the asteroid belt. The delivery of these molecules was constant in the early solar system as meteorites like Murchison rained down on the young planets. And Earth was not a closed system. It was seeded from the cosmos. But the story gets older, much older. Using incredibly sensitive techniques, scientists were able to isolate individual microscopic grains of silicon carbide and graphite from the meteorite's matrix. These grains are called prosolar grains, or more poetically, stardust. They are tiny crystals that condensed in the cooling outer layers of stars that died before our solar system was born. These stars, known as asymptotic giant branch AGB stars, puffed their carbon-rich atmospheres into space. In that outflow, tiny crystals of diamond, graphite, and silicon carbide formed. For millions of years, these grains drifted through the interstellar medium, the cold void between stars. Eventually, they were swept up into the giant cloud of gas and dust that would collapse to form our sun and its planets. That cloud was mostly hydrogen and helium, but it was seeded with these tiny, durable grains from a previous generation of stars. As the solar system formed, these grains were incorporated into asteroids, and for 4.6 billion years, they were locked away inside the rock that would one day become the Murchison meteorite. They are time travelers. By analyzing the unique isotopic ratios of elements like neon and xenon trapped inside them, scientists can calculate how long the grains were exposed to cosmic rays while traveling through interstellar space. This method gives a direct age. The oldest Murchison grain found so far is about 7 billion years old. It is the oldest solid material ever found on Earth. It is a physical piece of a star that died over 2 billion years before our planet even existed. Number 17, the first solids of the solar system. The Allende meteorite fell over Mexico in 1969, just months before Murchison. It was a massive event, scattering over 2 tons of material. Some of its white, blotchy inclusions are 4.567 billion years old, making them the oldest known objects formed within our solar system. These inclusions are so rich in certain elements that they must have condensed directly from the solar nebula at temperatures over 1300 degrees Celsius. On February 8, 1969, a brilliant fireball lit up the pre-dawn sky near Pueblito de Allende in Chihuahua, Mexico. It was described as a moving ball of fire as bright as the sun. The explosion that followed was heard for hundreds of miles, and it showered the desert landscape with thousands of black, fusion-crusted stones. It was the largest carbonaceous chondrite fall ever recorded. Unlike Murchison, which was a CM-type chondrite, Allende was a CV-type. The V stands for Vigorano, another meteorite, but it could just as well stand for very important. When scientists cut open the Allende stones, they saw a dark, fine-grained matrix peppered with small, round structures called chondrules. But they also saw something else. There were irregular, whitish-gray blobs and specks scattered throughout the rock. They looked out of place. These were the calcium-aluminium-rich inclusions, or CAIs. They are made of minerals like spinel and perovskite, which are stable only at very high temperatures. Analysis using lead dating, a highly precise method of radiometric dating, pinned down their age with incredible accuracy, 4.567 billion years. This is the benchmark. This is time zero for our solar system. These small, unassuming white specks are the very first solid objects to have condensed out of the hot gas of the solar nebula, the swirling disk of material that would eventually form the sun and planets. They are older than every planet, every moon, and every other asteroid. They are the building blocks of the building blocks. The existence of CAIs tells us a lot about the environment of the early solar system. It was not a calm, gentle place. It was a violent, hot furnace. The CAIs formed close to the young proto-sun, where temperatures were high enough to vaporize rock. As tiny droplets of this molten rock and mineral vapor were thrown away from the sun, They cooled and solidified into these strange refractory inclusions. Refractory means they have high boiling points. Lighter, more volatile elements like water and carbon would condense much later and much farther out in the cooler regions of the nebula. Allende was a treasure trove. It contained not just CAIs, but also microscopic diamonds. These were not the kind of diamonds formed under high pressure deep inside a planet. These were nanodiamonds so small that billions could fit on the head of a pin. They were formed in the explosive chaos of distant supernovae. Like the silicon carbide grains in Murchison, these nanodiamonds are presolar. They are another type of stardust, another physical link to the stars that came before our sun. The Allende meteorite is like a cosmic fruitcake, a dense mixture of the very first things to form in our own solar system, studded with even older remnants from stars that had lived and died long ago. Number 16, the mission to catch a comet's ghost. A spacecraft named Stardust traveled 3 billion miles to fly through the tail of a comet. It used a collector filled with a material called aerogel, a ghostly smoke-like solid that is 99.8% air. The mission successfully returned to Earth with samples of both comet dust and interstellar dust, the first of their kind. The idea was audacious. Most of what we learn about the cosmos comes from looking at it through telescopes. We analyze light, but what if we could actually reach out and grab a piece of it? A piece of something from beyond our own little neighborhood. In 1999, NASA launched the Stardust mission with exactly that goal. Its primary target was a comet named Wild 2. Comets are like dirty snowballs, leftovers from the formation of the solar system, preserved in the deep freeze of space for billions of years. By collecting dust from its tail, scientists hoped to get a pure sample of the early solar nebula. The collection method was ingenious, hitting a dust particle at 6.1 kilometers per second. 6 times the speed of a rifle bullet would normally vaporize it. To capture these particles gently, the spacecraft was equipped with a tennis racket-shaped collector filled with aerogel. This remarkable material, made of silicon, is the lightest solid known. When a particle hit the aerogel, it would bury itself, creating a long, carrot-shaped track and slowing down without being destroyed. In 2004, Stardust flew through the coma of Wild 2, its collector extended. It was a risky maneuver, but it worked. The spacecraft captured thousands of tiny comet particles, but that wasn't all. On its long journey, the spacecraft also exposed the other side of its collector to the void, pointing it in the direction the solar system is moving through the galaxy. The hope was to catch something even more exotic interstellar dust. These are the tiny grains that wander the space between stars, the same kind of presolar grains found in meteorites, but captured directly from space. In 2006, the sample return capsule detached from the main spacecraft re-entered Earth's atmosphere at a blistering 28,000 miles per hour and landed safely in the Utah desert. The real work then began. Thousands of citizen scientists, part of a project called Stardust Home, scoured millions of microscope images of the aerogel to find the telltale tracks of the captured particles. It was a needle in a haystack search. They found the comet particles, and they were full of surprises. They contained high-temperature minerals that should have formed close to the sun, not in the cold outer regions where comets are born. This suggested that the early solar system was a much more dynamic place than previously thought, with material from the inner solar system being thrown out to the far reaches. Then, after years of searching, they found them. 7 tiny, precious particles of interstellar dust. These were the first samples of our galaxy's raw material ever brought to a lab. One grain, nicknamed Inti after the Inca sun god, was made of a magnesium-iron silicate compound. Analysis showed it had a unique crystalline structure, one that suggested it had been altered by radiation during its long journey through space. These particles are direct proof of the cosmic cycle of matter. They were forged in distant stars, drifted for millions of years, were captured by a human-made probe, and are now sitting in a laboratory on Earth. They are pieces of the galaxy that are by their very nature older than our world. Number 15, the strange stone from the Libyan Desert. A small black stone found in the Egyptian desert in 1996 is unlike any other object ever found on Earth. It is named the Hypatia stone. It is made of a bizarre matrix of microdiamonds and contains minerals and chemical ratios that match no known meteorite or comet. Some scientists believe it may be a fragment of a comet nucleus that predates the formation of the solar system. The story of the Hypatia stone begins in December 1996, when an Egyptian geologist named Ali Barakat was surveying in southwestern Egypt. He stumbled upon a field of Libyan desert glass, a beautiful yellow silica glass, formed by a massive meteorite impact 29 million years ago. But among the glass, he found one peculiar pebble-sized black stone. It was light, porous, and covered in a strange, shiny crust. He knew it was something different. He took it back to his lab. The initial analysis was baffling. The stone was carbon-rich, but its structure was completely alien. It wasn't a standard meteorite. It didn't fit into any of the established categories. For years, the stone, now named Hypatia after the ancient female philosopher and astronomer of Alexandria, remained a mystery. In 2013, a team of researchers from the University of Johannesburg began a new intensive study. What they found only deepened the puzzle. The stone's internal structure was like a compressed jumble of material. The bulk of it was a carbon-rich matrix, but not graphite like in many meteorites. It was a matrix packed with microscopic diamonds. These were likely formed by the shock of impact with Earth's atmosphere or surface. But what was embedded in this diamond matrix was even stranger. They found grains of moissanite silicon carbide in a highly unusual form. They found nickel phosphide, a mineral never before found in any object in our solar system. They found pure metallic aluminum, which is incredibly rare in nature. The chemical recipe was just as weird. All the objects in our solar system, planets, asteroids, comets, were formed from the same well-mixed cloud of dust and gas, the solar nebula. As a result, they share a broadly similar chemical composition. Certain elements always appear in certain ratios to others. Hypatia breaks these rules. It has a huge amount of carbon and very little silicon, the opposite of a typical rocky object. The ratios of other elements are all over the place, matching nothing. The conclusion the research team came to was radical. Hypatia is not from the inner solar system. It's not from the asteroid belt, it's not from the Kuiper belt or the Oort cloud, the reservoirs of comets at the edge of our system. The material that formed Hypatia seems to have avoided the great mixing that created our solar system. The researchers proposed that the stone is a fragment of a comet's nucleus, but one whose ingredients were never homogenized with the rest of the solar nebula. Its components, the dust and gas it formed from, might represent a pure, unaltered sample of the interstellar medium that existed before our sun was born. If true, the Hypatia stone is not just a rock older than Earth. It is a fossil of the very cloud that gave birth to our solar system, a piece of pre-solar stuff that somehow survived its fiery plunge to Earth. Number 14, the controversy of life in a French meteorite. The Orgueil meteorite fell in southern France in 1864. It is a carbonaceous chondrite extremely rich in water and organic compounds. In the 1960s, a study claimed to have found organized elements resembling fossilized microorganisms inside the meteorite, sparking a huge controversy about extraterrestrial life. On the evening of May 14, 1864, a spectacular fireball flew over France, breaking up and scattering about 20 black stones near the town of Orgueil. It was an immediate scientific sensation. This was a rare type of meteorite, a CI chondrite. CI chondrites are considered the most primitive of all meteorites. Their chemical composition almost perfectly matches the composition of the sun's photosphere, excluding the volatile gases like hydrogen and helium. They are essentially unaltered chunks of the primordial solar nebula. They are rich in water, bound up in clay minerals, and full of complex organic carbon compounds. Because of this, Argyll was a prime target in the search for extraterrestrial life. In the early 1960s, a team of scientists published a paper claiming to have found microscopic structures within the meteorite that they called organized elements. They looked like tiny fossilized algae or bacteria. The paper caused a firestorm. Had life been found in space? The implications were enormous. However, other scientists were skeptical. They re-examined the Argyll samples. The organized elements turned out to be a mix of things. Some were earthly pollen grains and fungal spores that had contaminated the sample over the century. It had been sitting in a museum. Others were just mineral crystals that happened to look vaguely biological. The most famous fossil was found to be embedded in the meteorite with glue and was part of a common European plant. It was clear that at some point someone had intentionally or unintentionally contaminated the sample, perhaps as a hoax. The controversy died down, and the claim of fossils in Argyll was thoroughly debunked. But the meteorite's importance did not diminish. The fiasco taught the scientific community a crucial lesson about the dangers of contamination, a lesson that would be vital for analyzing moon rocks and other meteorites like Murchison later in the decade. Even without fossils, Argyll is a window into the time before Earth. It contains a rich suite of abiotic organic molecules, including amino acids, confirming that these compounds are common in the raw materials of planets. It also contains presolar grains of diamond and graphite, tiny messengers from dead stars. The water trapped in its clay minerals has an isotopic signature, the ratio of deuterium to hydrogen, that is very similar to the water in Earth's oceans. This suggests that a significant portion of Earth's water may have been delivered by impacts from primitive, water-rich asteroids like the one that produced the Argyll meteorite. So while it may not carry life, it carried the ingredients, the carbon, the water, and the building blocks, all from a time before our planet had fully formed. On number 13, a fresh delivery from the ancient past. In April 2019, a meteorite fell in the rainforests of Costa Rica near the town of Aguas Zarcas. It was a carbonaceous chondrite, very similar to the Murchison meteorite. Because it was collected so quickly from a clean environment, it represents one of the most pristine samples of the early solar system ever studied. It is filled with complex organic molecules that have not been altered by Earth's environment. The story of Aguas Zarcas is the modern version of the Murchison Fall. On April 23, 2019, a bright fireball was seen over Costa Rica. It fragmented, and for the next few days, residents of the Aguas Zarcas region found small charcoal-like rocks on their properties. One woman heard a crash and found a 280-gram stone had smashed through the roof of her dog's house. Meteorite hunters and scientists rushed to the area. This was a scientific jackpot. The meteorite was a CM2 carbonaceous chondrite, the same type as Murchison, but Murchison fell 50 years earlier. It had been handled, stored, and analyzed with the technology of the 1970s. Aguas Zarcas was fresh. It fell in a rainy but relatively unpolluted area. The fragments were collected within days before significant weathering or contamination could occur. They were sealed in bags and rushed to state-of-the-art laboratories. This gave scientists an unprecedented opportunity. They could study the most delicate and volatile organic compounds, the ones that might have been lost or altered in older meteorite samples. The initial analyses were thrilling. The rock was packed with a huge variety of organic molecules. They found amino acids, just like in Murchison, with an equal mix of left and right-handed versions, proving their extraterrestrial origin. But they also found more complex compounds, including sugars and the precursors to nucleotides, the components of RNA and DNA. The Aguas Zarcas meteorite is essentially a 4.56 billion-year-old piece of clay. It's a soft, fragile rock, barely held together. This fragility is a sign of its primitive nature. It has never been significantly heated or altered since it first formed in the solar nebula. The water trapped within its minerals tells a story of the outer solar system where ice was plentiful. The organic molecules tell a story of cosmic chemistry, of simple molecules being irradiated by starlight and forming more complex structures in the cold of space. Studying Aguas Zarcas is like having a time machine. Scientists can analyze it with instruments that were unimaginable in 1969. They can map the organic molecules within the rock structure, seeing how they are associated with different minerals. This helps them piece together the chemical processes that were happening in the disk of gas and dust that surrounded the young sun. It confirms that the delivery of life's raw materials to the early Earth was not a rare event. The solar system was filled with objects like the Aguas Zarcas parent body carrying water and a rich inventory of organic chemistry ready to seed any rocky planet in the right location. It is a direct sample of the stuff from which we are made, preserved for eons before falling into our hands. Number 12, the black rock from a frozen Canadian lake. In January 2000, a fireball lit up the skies over British Columbia and the Yukon in Canada. It landed on the frozen surface of Tagish Lake. The extreme cold and the quick, careful recovery preserved the meteorite in a near-perfect state, preventing almost all terrestrial contaminations. It is one of the most primitive, unaltered meteorites ever found. The Tagish Lake meteorite fall was a stroke of luck. On January 18th, 2000, a massive fireball, estimated to have the energy of several kilotons of TNT, exploded in the upper atmosphere. The event was seen and recorded by satellites and witnesses over a vast, sparsely populated area. Over the next week, a local resident named Jim Brook ventured out onto the frozen, snow-covered surface of Tagish Lake and began finding small, dark fragments of the meteorite. He recognized what they were, and crucially, he knew how to handle them. He collected the fragments without touching them directly, using clean plastic bags. He kept them frozen. This was incredibly important. The Tagish Lake meteorite is a type of carbonaceous chondrite, so fragile and porous that it is almost like a lump of charcoal or dried mud. If it had landed in a field and been rained on, it would have disintegrated. If it had been handled, it would have been instantly contaminated. By keeping it frozen, all of its original volatile chemicals, including water ice and delicate organic compounds, were preserved. When scientists got the samples into their clean labs, they realized they had something special. It was designated a CICM2 chondrite, a unique type that bridges two of the most primitive meteorite classes. Its chemical makeup is even closer to the sun's composition than the famous Allende meteorite. It is essentially a fossil of the primordial solar nebula, a chunk of ice and dust that has remained largely unchanged for 4.5 billion years. The organic material in the Tagish Lake meteorite is particularly interesting. It is full of hollow, bubble-like spheres of organic carbon, called organic globules. These microscopic structures are not life, but they show how organic molecules in the early solar system could spontaneously form membranes and compartments. The ability to form a boundary, to separate an inside from an outside, is a critical first step towards the origin of life's first cells. The meteorite provides a snapshot of this prebiotic chemistry in action. The dust that makes up the Tagish Lake meteorite is also ancient. Like other primitive chondrites, it contains a population of prosolar grains. These tiny specks of silicon carbide, graphite, and nanodiamonds were forged in stars that existed before our sun. They were incorporated into the icy body that became the Tagish Lake parent asteroid in the cold, outer reaches of the solar system. The meteorite is a direct sample of the outer solar nebula, a region that is difficult to study directly. It tells us that the ingredients for life were not just present in the asteroid belt, but were likely widespread throughout the entire protoplanetary disk, offering a chemical toolkit for every planet that formed. Number 11, the messenger from the red planet. A meteorite designated Allen Hills 84001 was found in Antarctica in 1984. It is a piece of the planet Mars blasted into space by an ancient asteroid impact. The rock itself is extremely old, having crystallized from Martian lava 4.1 billion years ago. In 1996, a team of NASA scientists announced they had found evidence of fossilized microscopic life within the rock, creating a global scientific and political sensation. The story of ALH 84001 is a scientific drama. It was one of thousands of meteorites collected from the blue ice fields of the Allende Hills in Antarctica, a pristine environment where dark meteorites stand out clearly and are preserved by the cold. For a decade, it sat on a shelf, misidentified as a common type of asteroid. Then, in 1994, a closer look revealed its true identity. It was a Martian. We know this because tiny pockets of gas trapped within the rock's glass match the unique atmospheric composition of Mars, which we have measured with our landers. But this was no ordinary Martian meteorite. Most Martian meteorites are young, geologically speaking, around 1.3 billion years old. A radiometric dating of ALH 84001 showed it was a staggering 4.1 billion years old. It formed from cooling magma on a very young Mars, a time when the planet was likely warmer and wetter and potentially more hospitable to life. The rock was then blasted off Mars by a major impact about 17 million years ago, drifted through space, and landed in Antarctica about 13,000 years ago. The real excitement began in 1996. A team from NASA Johnson Space Center, led by David McKay, published a paper in the journal Science. They presented 4 lines of evidence that they believed pointed to the presence of ancient fossilized life in the meteorite. They had found complex organic molecules called polycyclic aromatic hydrocarbons, PAHs. They found tiny grains of magnetite and iron sulfides, minerals that on Earth can be produced by bacteria. And most visually compelling, they used powerful electron microscopes to find tiny, segmented, worm-like structures that they interpreted as nanofossils, the mineralized remains of ancient Martian microbes. The announcement was huge. The President of the United States gave a speech about it. It was front-page news around the world, but the scientific community immediately began to scrutinize the evidence with intense skepticism, which is the proper role of science. Over the following years, non-biological explanations were proposed for every line of evidence. The PAHs could be from terrestrial contamination or formed by non-living processes. The mineral grains could have formed through high-temperature events, like the shock of the impact that launched the rock into space. And the nanofossils, the most tantalizing evidence, were shown to be potentially just strangely shaped mineral growths or artifacts of the imaging process. They were also far smaller than any known cellular life on Earth. Today, the consensus is that ALH 84001 does not contain definitive proof of Martian life. The evidence is ambiguous at best. However, the debate it sparked was incredibly productive. It pushed forward the entire field of astrobiology, forcing scientists to define what would constitute real proof of extraterrestrial life. And the rock itself remains an invaluable scientific object. It is a piece of Mars from a time when Earth itself was just getting started. It is a 4.1 billion year old chunk of another world, a piece of cosmic debris that is not older than the solar system, but is one of the oldest planetary rocks we have ever held. It's a relic from the era when, life first arose in our solar system, whether on one world or two. Number 10, diamonds from before the sun. Many primitive meteorites contain diamonds, so small they are measured in billionths of a meter. These are not the high-pressure gems we know on Earth. They are prosolar grains formed in the turbulent, carbon-rich environments around exploding stars called supernovae. They are the most abundant type of prosolar grain, and they carry the chemical signature of the violent stellar events that created the heavy elements necessary for life. When we think of diamonds, we think of something rare and precious. But in the context of the cosmos, some diamonds are incredibly common. It's found embedded in meteorites like Allende and Murchison are vast numbers of nanodiamonds. Well, a single gram of such a meteorite can contain a quadrillion of these tiny crystals. They are far too small to be seen with a normal microscope. Finding and analyzing them requires dissolving away almost the entire meteorite with powerful acids, leaving behind only the most chemically resistant materials, including these tiny diamonds. Their origin was a long-standing puzzle, but the key came from analyzing the isotopes of noble gases like xenon that were trapped inside the crystal lattices of the diamonds as they formed. They contained a very specific isotopic signature known as xenon HL. This particular mix of xenon isotopes can only be produced in the extreme conditions of a supernova explosion. This was the smoking gun. These diamonds were not formed in the solar nebula or inside an asteroid. They were formed in the heart of a cosmic catastrophe. A supernova is the explosive death of a massive star. In its final moments, the star forges a huge quantity of heavy elements through a process called explosive nucleosynthesis. The star then blows itself apart, seeding the surrounding space with these newly made elements, including a lot of carbon. In the shockwaves and the cooling, turbulent debris of the supernova, conditions are right for carbon atoms to link up and form these tiny, stable diamond crystals. For millions of years, these nanodiamonds, carrying their cargo of supernova-forged xenon, drifted through the interstellar medium. They became part of the raw material of the galaxy. When the molecular cloud that would become our solar system began to collapse, these diamonds were part of the mix. They were incorporated into the dust and ice that formed the planetesimals and asteroids. These tiny diamonds are therefore direct messengers from the violent stellar events that enriched our corner of the galaxy. The iron in our blood, the calcium in our bones, the oxygen we breathing, all of these heavy elements were created inside stars and spread through space by supernovae. The prosolar nanodiamonds found in meteorites are a physical remnant of that process. They are older than the sun and the earth, and they are a tangible link to the stellar explosions that made our existence possible. They are not just cosmic debris, they are the debris of our own creation story. And number 9, the stardust made of silicon carbide. Besides diamonds, another major type of prosolar grain found in meteorites is silicon carbide, or moissanite. These microscopic crystals are tougher than diamonds and are formed in the atmospheres of a different kind of dying star carbon-rich AGB stars. Each grain is a tiny time capsule containing the specific isotopic fingerprint of its parent star, allowing scientists to study individual stars that died billions of years ago. Silicon carbide IC grains were among the first prosolar grains to be definitively identified in the late 1980s. They are much rarer than the nanodiamonds, but are, typically larger, which makes them easier to study individually. They are found by dissolving a meteorite sample in acid. The tough SiC grains are left behind. Their origin is not in supernovae, but in a more common type of star death. They come from asymptotic giant branch, or AGB, stars. These are stars like our sun will become in about 5 billion years. After a star exhausts the hydrogen fuel in its core, it swells up into a red giant. In the later stages of this process, for stars of a certain mass, a process called dredge-up brings carbon from the core to the surface. The star becomes a carbon star with more carbon than oxygen in its atmosphere. In the cool outer layers of these pulsating stars, the conditions are right for the carbon atoms to combine with silicon atoms, forming tiny crystals of silicon carbide. The star's stellar wind then blows these grains out into interstellar space. They are literally stardust. What makes these sick grains so valuable to science is that each one is a pristine sample of its parent star's atmosphere. By using incredibly sensitive instruments like a NanoSIMS ion probe, scientists can blast a tiny beam of ions at a single SiC grain and measure the isotopic composition of the material. Different stars produce different ratios of isotopes depending on their mass and the nuclear reactions happening in their cores. This is like stellar archaeology. By analyzing the isotopic ratios of carbon, nitrogen, and silicon in a single grain, scientists can tell what kind of star it came from. Most come from AGB stars, but Some rare types show the isotopic signatures of supernovae or even more exotic stellar events like novae. It's like having a collection of sand where each grain comes from a different specific volcano somewhere in the world, and you can trace it back to its source. These grains are survivors. They endured the death of their parent star, a long journey through the harsh environment of interstellar space where they were bombarded by cosmic rays, the chaotic formation of our solar system, and billions of years locked inside an asteroid. They are tiny, indestructible messengers that carry the detailed story of the galaxy's chemical evolution, star by star. Each one is a piece of cosmic debris older than the Earth, a speck of a star we can hold and study in a lab. Number 8, a Frankenstein's monster from the dawn of the solar system. The Ishayevo meteorite, found in Russia in 2003, is one of the strangest meteorites known. It is a chimeric meteorite, a jumble of at least 3 completely different meteorite types welded together. It contains metal-rich fragments, rocky chondritic fragments, and inclusions that seem to come from a different class of meteorite altogether. It is a snapshot of the violent, messy collisions that occurred as the planets were first beginning to form. Most meteorites are relatively uniform. They are a single type of rock, but Ishayevo is different. It's a jumble. The main body of the meteorite is a CBB chondrite, a type characterized by having a lot of metal and large barred chondrules, suggesting it was formed in a high-energy event, possibly the vapor plume from a massive impact between planetesimals. But embedded within this material are chunks of something else. There are fragments that look like a completely different type of meteorite, a CH chondrite. These are also metal-rich, but have different characteristics, and scattered throughout are inclusions called ultrafactory inclusions, which contain minerals that form at even higher temperatures than the CAIs in the Allende meteorite. These inclusions must have formed in the hottest, innermost part of the solar nebula. Ishayevo is like a geological Frankenstein's monster. It is a single rock made of parts that formed in different places and under different conditions in the early solar system, which were then violently smashed together into one object. This provides powerful evidence for the modern model of planet formation, which is not a gentle, slow accretion, but a chaotic and violent process of collisions. The age of the components in Ishayevo is also remarkable. The various chondrules and inclusions have been dated to the very beginning of the solar system, around 4.567 billion years ago. They represent a mix of materials that were present in the solar nebula within the first few million years of its existence. The meteorite itself was likely assembled during a catastrophic impact between 2 early asteroid-like bodies. The heat and pressure of this event welded the disparate pieces together. Studying Ishayevo is like being an archaeologist at a crash site. Each different component tells a part of the story. The CH fragments tell of one parent body, the CBD matrix tells of another. The ultra-refractory inclusions tell of the conditions very close to the young sun. The fact that they are all found together in one rock tells of the immense collisions that were common in the crowded early solar system. And it's a piece of debris from the construction site of the planets, a jumble of leftover bricks and mortar that contains some of the oldest solid materials we have ever found. Number 7, the pristine relics of Efremovka. The Efremovka meteorite was found in Kazakhstan in 1962. It is a CV-type carbonaceous chondrite, similar to Allende. However, its calcium-aluminium-rich inclusions, CAIs, are considered to be some of the most pristine and unaltered ever found. They have not been subjected to the same degree of heating and chemical alteration that affected the CAIs in Allende, giving us an even clearer view of the solar system's first moments. While Allende is the most famous meteorite for studying CAIs, the very first solids of the solar system, it is not perfect. The Allende parent body experienced some thermal metamorphism. a gentle heating that occurred within the asteroid over millions of years. This process slightly altered the minerals in the CAIs, blurring the record of their initial formation. Efremovka is different. It is a more pristine sample. Its CAIs show very little evidence of this secondary heating. They are sharper, clearer snapshots of condensation from the solar nebula. They are like a first-generation photocopy, while Allende's are like a second or third. One of the most important discoveries from Efremovka's CAIs relates to the timeline of the early solar system. By using extremely precise dating techniques on different minerals within a single CAI, scientists can create a detailed history. They found that these objects contain evidence of short-lived radioactive isotopes like aluminum-26. Aluminum-26 has a half-life of only about 717,000 years. This is very short in cosmic terms. The fact that it was present when the CAIs formed means that a nearby supernova or massive star must have seeded the solar nebula with freshly synthesized radioactive material just before or during its collapse. This provides a crucial piece of the puzzle of our solar system's birth. It suggests that the collapse of our parent molecular cloud was not a spontaneous event, but was likely triggered by the shockwave from a nearby exploding star. The Efremovka CAIs contain the fingerprints of this trigger event, locked in their mineral structure. Furthermore, studying the pristine oxygen isotope ratios in Efremovka's inclusions has helped scientists map out the different chemical environments in the solar nebula. The nebula was not a uniform, well-mixed soup. There were different regions with different isotopic compositions, likely due to chemical reactions involving ultraviolet light from the young sun. The CAIs in Efremovka captured this pristine isotopic signature before it could be erased by later processing. They are some of the cleanest and oldest relics we have from the birth of our planetary system, a direct link to the moments when gas first turned to solid. Number 6. The twisted story of Leoville's inclusions. The Leoville meteorite, which fell in Kansas in 1961, is another CV3 carbonaceous chondrite. What makes it special is that many of its calcium-aluminium-rich inclusions, CAIs, are strangely deformed. They appear to have been squashed, stretched, and folded while they were still hot and plastic. This tells a story of violent events and collisions happening in the solar nebula at the very beginning, even as these first solids were forming. The CAIs found in meteorites like Allende and Efremovka are typically irregular blobs or spheres. They look like they condensed from a gas and then floated freely in space. But many of the CAIs in the Leoville meteorite look different. They are flattened and elongated, their internal layers of minerals are bent and folded, they look like they were squeezed. This observation puzzled scientists for a long time. How could these objects, which formed at high temperatures, get deformed? The current leading theory is that they experienced collisions while they were still hot and malleable in the first few million years of the solar system's existence. The solar nebula was not a tranquil place. It was a crowded, turbulent disk of gas, dust, and newly forming objects. The planetesimals were smashing into each other, shock waves were propagating through the gas. The deformed CAIs of Leoville are evidence of this chaos. They seem to have been caught in collisions between early planetesimals or perhaps passed through powerful shock waves in the nebula. The impacts were not catastrophic enough to destroy them, but they were strong enough to deform them, like a potter squeezing a soft clay pot. This provides a dynamic picture of the early solar system. The very first solid objects were not just forming and then gently accreting. They were being processed, battered, and reshaped by their violent environment. The Leoville meteorite captured a snapshot of this processing. It picked up a population of CAIs that had gone through this rough and tumble phase and preserved them for billions of years. Studying the precise nature of the deformation, the way the crystal layers are bent, can tell scientists about the pressures and temperatures involved in these early impacts. It helps them build better models of how dust and pebbles stuck together to form larger and larger bodies a critical but poorly understood step in planet formation. Leoville is a testament to the fact that our solar system was forged in violence. Its oldest components bear the scars of that chaotic birth. Number 5, the Kansas meteorite and its unique chondrules. The Kansas meteorite fell in Russia in 1937. It is a CO3-type carbonaceous chondrite, a different group from the CV and CM types. CO chondrites are known for their very small chondrules, tiny spheres of once molten rock. The study of Kansas and its components provides another distinct window into the conditions and processes that were occurring in the solar nebula in a different region or at a different time from where other meteorites formed. While all chondritic meteorites contain chondrules, the characteristics of those chondrules vary. In the Kansas meteorite, the chondrules are notably small, typically less than 0.2 millimeters in diameter. This is a key distinguishing feature of the CO group. The size of chondrules is thought to be related to the conditions under which they formed things like the density of dust particles and the cooling rate of the molten droplets. The small chondrules in Kansas suggest it formed in a different part of the solar nebula than meteorites like Allende, which have much larger chondrules. Kansas is considered one of the least altered members of its group, meaning it's a very primitive sample. Like other carbonaceous chondrites, it contains water-bearing minerals and a rich inventory of organic matter. It also contains CAIs and persolar grains, firmly establishing its credentials as a carrier of material older than the Earth. One of the fascinating aspects of meteorites like Kansas is what they tell us about the Great Divide in the early solar system. There appears to have been a separation between the inner solar system where the rocky planets formed and the outer solar system where the gas giants formed, possibly due to the formation of Jupiter. These two regions had different chemical and isotopic compositions. Meteorites are grouped into carbonaceous and non-carbonaceous clans that seem to originate from these two different reservoirs. Kansas, as a carbonaceous chondrite, is a sample from the outer reservoir. Its specific chemistry helps us define the composition of the material beyond the asteroid belt, the stuff that went on to form the cores of the giant planets. By comparing the detailed mineralogy and isotopic makeup of Kansas to other meteorites like Allende, a CV from the outer group, and ordinary chondrites from the inner group, scientists can piece together a map of the early solar system. Each meteorite type is a data point from a different location. Kansas, with its tiny chondrules and primitive composition, is a crucial pin on that map representing a specific set of conditions in the vast swirling disk from which the planets were born. Number 4, the graphite grains from red giant stars. Along with diamonds and silicon carbide, a third major type of persolar dust found in meteorites is graphite. Graphite is a pure form of carbon, the same material found in a pencil lead. These persolar graphite grains are typically spherical, like tiny onions with concentric layers of carbon atoms. They formed in the outflows of carbon-rich AGB stars and supernovae, and like other persolar grains, they carry the isotopic signature of their stellar homes. Finding persolar graphite grains is a similar process to finding other stardust. Scientists take a piece of a primitive meteorite, dissolve it in acids that destroy silicate minerals and other compounds, and are left with a residue of tough carbon-based materials. Among these are the tiny graphite spherules. Their onion-like structure is a clue to how they formed. They likely nucleated and grew layer by layer in the cooling carbon-rich gas flowing away from a dying star. What makes them particularly valuable is what can be trapped inside them. As these graphite shells grew, they sometimes encapsulated other, even smaller crystals. Scientists have found tiny crystals of titanium carbide and silicon carbide tucked away inside a protective graphite coating. This is like a Russian nesting doll of stardust. The inner crystal formed first, then was wrapped in layers of graphite. This protects the inner grain from being altered or destroyed, preserving an even purer sample of the stellar environment. The isotopic compositions of these tiny nested crystals can be analyzed, providing incredibly detailed information about the sequence of condensation and the changing conditions in the stellar atmosphere. Some of these graphite grains have very strange isotopic ratios, particularly of carbon and oxygen, that point to a more exotic origin than a standard AGB star or supernova. A few grains are thought to have come from nova. A nova is an explosion on the surface of a white dwarf star that is pulling material from a companion star. These events also create unique isotopic signatures, and finding a presolar grain that matches these signatures is a powerful confirmation of our models of stellar explosions. Like all presolar grains, the graphite dust is a direct physical link to a previous generation of stars. They drifted for millions of years in the void before being caught up in the formation of our solar system. They are part of the 1% of our solar system's material that is not from our sun. They are alien dust, older than our planet, and they carry the stories of the stars that enriched the galaxy with the carbon that is now the basis of all known life. Number 3, Black Beauty and the Ancient Crust of Mars. A meteorite found in the Sahara Desert in 2011, designated Northwest Africa NWA 7034 and nicknamed Black Beauty, is a unique type of Martian meteorite. It's not a single rock type but a breccia, a collection of different rock fragments cemented together. Some of the fragments inside it are pieces of the ancient Martian crust, and they contain zircon crystals that have been dated to be as old as 4.48 billion years. Black Beauty is a stunningly beautiful meteorite with a dark matrix studded with lighter colored crystals and rock fragments. It is the only brecciated Martian meteorite we have, which makes it incredibly valuable. Instead of representing a single lava flow, it represents a sample of the Martian surface, a kind of Martian soil that has been lithified into a rock. It contains fragments of basalt, bits of impact melt, and various minerals. The most important components for understanding ancient Mars are the tiny, durable crystals of zircon. Zircon is a fantastic mineral for geologists because it incorporates uranium but rejects lead when it crystallizes. This makes it perfect for uranium-lead dating, one of the most precise dating methods available. When scientists found zircons in Black Beauty and dated them, the ages came back as old as 4.48 billion years. This is an astonishingly old age for a planetary crust. It means that Mars had a solid, differentiated crust just 100 million years after the solar system began to form. This is much faster than the Earth's crust is thought to have stabilized. These tiny zircon crystals are the oldest pieces of Mars we have ever been able to study. They tell us more than just the age of the crust. The chemical composition of the zircons provides clues about the environment in which they formed. They suggest that the magma they crystallized from was rich in water. This provides strong evidence that early Mars was a water-rich planet long before the period when we see evidence of rivers and lakes. Black Beauty itself was formed much later. The various ancient fragments were jumbled together and cemented into a single rock by a volcanic or impact event about 1.5 billion years ago. Then, a much more recent impact, only about 5 to 10 million years ago, blasted it off the surface of Mars and sent it on its journey to Earth. While the rock itself is not older than the Earth, the zircon crystals preserved within it are. They are 4.48 billion-year-old relics from the earliest history of another planet. And they are older than the oldest known rocks on Earth. They are pieces of cosmic debris from our next-door neighbor, providing a window into the first 100 million years of planetary evolution, a period from which almost all of Earth's own rock record has been erased. Number 2. The cosmic dust in your attic. Every day, about 100 tons of cosmic material falls to Earth. Most of it is in the form of tiny dust particles called micrometeorites. These particles are everywhere on rooftops, in rain gutters, and at the bottom of the ocean. Most of these particles are from our own solar system, but a tiny fraction of them are true interstellar dust, the same kind of prosolar grains found inside meteorites. You don't need to wait for a meteorite to fall to find material older than the Earth. You just need a magnet and a microscope. For decades, scientists have collected micrometeorites from the cleanest places on Earth, like the deep sea floor or the snows of Antarctica. These tiny melted spheres, typically smaller than a millimeter, are the remnants of small dust particles that burned up as they entered the atmosphere. More recently, a Norwegian amateur scientist, John Larsen, pioneered a method for finding them in urban environments. By painstakingly sifting through sediment collected from rooftops and rain gutters, he was able to identify and isolate modern micrometeorites, proving they could be found even in a city. The vast majority of this dust comes from asteroids and comets within our solar system. They are debris from the formation of the planets, about 4.5 billion years old, but a small, elusive fraction of this dust has a different origin. Just as the Stardust mission captured interstellar dust in space, Earth itself is constantly sweeping up this material as it orbits the sun. Identifying these interstellar dust particles is incredibly difficult. They are mixed in with billions of terrestrial dust particles and solar system micrometeorites. But scientists have succeeded. By analyzing particles collected by high-altitude research aircraft, they have found tiny, fluffy particles with chemical and isotopic compositions that are not solar. They are rich in specific isotopes that point to an origin in the atmospheres of distant evolved stars. These particles are fragile. Unlike the tough, durable grains found inside meteorites, which were protected by the surrounding rock, these particles have been exposed directly to space. They are often porous aggregate structures. Studying them gives us a different perspective on the nature of interstellar dust. So scattered all around us, in the dust, on our streets, and the sediment in our oceans, are tiny, invisible specks of matter that are older than the sun. They are the same material that formed the molecular cloud from which our solar system was born. Earth is constantly being dusted with the ashes of long-dead stars. We are living in a continuous, gentle rain of cosmic debris that predates our very world. Number 1, the building blocks of ourselves. The most profound piece of cosmic debris, older than the Earth, is not a single rock or a specific type of dust. It is a concept proven by all the others. It is the complex organic molecules themselves. The amino acids, the sugars, the nucleobases, the very components that make up life are not a product of Earth. They are a product of the cosmos. They formed in the cold interstellar medium and in the solar nebula long before Earth existed. The discovery of amino acids in the Murchison meteorite in 1969 was the first major piece of evidence. The fact that there was a mix of left and right-handed molecules proved they were formed by non-biological chemistry in space. Since then, we have found these molecules in many other meteorites. We have detected them in the giant molecular clouds between stars using radio telescopes. We have found them in the tails of comets. This tells us something fundamental about our own origins. The raw materials for life are not rare or special. They are ubiquitous. The universe is a prolific organic chemist. In the cold, diffuse clouds of gas and dust between stars, simple molecules like water, ammonia, and methane are frozen onto the surfaces of dust grains. Over millions of years, the faint but persistent ultraviolet light from distant stars provides the energy to break these molecules apart and allow them to recombine into more complex structures. This slow, patient chemistry creates a rich inventory of organic compounds. When these clouds collapse to form new stars and planetary systems, this organic material is included. It gets incorporated into asteroids and comets. In the early days of the solar system, these objects constantly bombarded the young planets. This late veneer of material delivered not only water to the early Earth, but also a rich supply of the organic building blocks needed for life to begin. So, the carbon atoms in your proteins, the complex molecules that form the basis of your cells, have a history that stretches back before the Earth. Those atoms were forged in the core of a star that lived and died before our sun. They were spewed out into space, floated in an interstellar cloud, and participated in the slow dance of cosmic chemistry to form amino acids and other complex molecules. Those molecules were then incorporated into an asteroid, which eventually delivered them to a young, barren Earth. This is the ultimate legacy of studying these ancient rocks. They show us that we are not separate from the cosmos, we are a direct product of it. The line between geology, chemistry, and biology blurs and disappears. The story of life on Earth does not begin on Earth. It begins in the cold, dark spaces between the stars, with the formation of dust grains and organic molecules that are older than our planet itself. The most ancient cosmic debris is, in a very real sense, us.